Hello and welcome back to the Applied Deep Learning course with a brief introduction into the topic. I'd like to start with a question to you. So when you take a look at this email that I received recently, do you think this is spam? Congratulations, you've won 650,000 euros in a monthly Euro Millions Google promo lottery on April 26th, 2019. Please consult us to claim your winnings with the following information: your full name, address, birthday, and of course, your credit card number. Well, I think it's pretty obvious that this is spam, like monthly lottery winnings and so on and so forth. So it's quite suspicious. But the question is, what about this email? Greetings. Hi, Mr. Margaret Ko-Mai-Lee Lung, Deputy Chairman, Managing Director, and Executive Director of Chongqing Bank Limited. I write briefly to seek your collaboration in a multi-million transaction with good return for us on participation. Reply for details. Well, if you read about it, sure, it's spam as well. But how do we know? And especially the more interesting question is, how would a computer know? Because for the first email was quite clear. Someone was asking for credit card information with a large sum of money. So if we would like to write a spam detection system, we could probably feed in some keywords that appeared in the first email that would make it clear this is spam with a very high chance. For example, the large sum of money, the credit card number, someone who say you won the lottery, and all of that stuff. So it would be quite easy to say, here are my set of rules, therefore this is very likely spam. But with this email, it's much more tricky. I mean, you actually have to understand the content of this multi-million transaction. Well, I mean, imagine that you're working in a bank. Who says that you're not on a day-to-day basis handling multi-million transactions? So the thing is, we need some context. We need information. We need to understand what is going on to have an informed decision whether this is spam or not. A completely different story. What do you see here? I hope you see a cat, and it's quite obvious, but again, can you ask the computer to tell you what the computer sees here? I think this is a pretty challenging task if you think about programming such a program. Imagine someone tells you, please write a program that detects cats and distinguishes them from dogs, for example. Then you might sit down, you try to come up with a clever algorithm which does something like it tries to find the edges, maybe the contour, and then you might do some template matching. But I mean, honestly, I think it's super hard to determine what makes this cat a cat for us. I mean, for us it's immediate because we've seen millions of photos and actual cats in our life probably. Well, maybe not millions of cats, but if you think about it, we've seen so many cats and dogs in our life, and we learned to distinguish them. But the computer, if you try to come up with a set of rules, it will be really hard to do this. And people have done it in the past. There were a couple of competitions where they were trying to program classifiers for bicycles and cars and other stuff. And on an annual base, they met in their conferences, and then they joked maybe a little bit about, oh yeah, this year my car category is better than yours, but your bicycle is worse than mine, and so on and so forth. So it's quite hard to solve this if you try to come up with a set of rules. And I mean, sure, there are examples that I wouldn't take too serious, like this lovely example of dogs that look like muffins. But in general, I think it's really, it drives down the point that imagine you have to find some interesting parts here that make this a muffin or make this a dog. I mean, what features do you think would make this a dog or a muffin? For example, the sugar in the in the muffin on the right, sure, that's a clear indicator. But then how do you know that there is sugar in the image? Or how do you know that there are eyes? I mean, eyes are a very strong indicator for animate objects, in this case dogs. But if you just try to detect black blobs, black circles, well, the muffins will also fall into that category. So the problem that I'm trying to tell you that we're facing is that some problems are too tough to write them down as a set of rules. It becomes really, really hard if you think about trying to detect a cat. What rules determine whether this is a cat or something else? And this empirical programming, where you say, do this, do that, quickly reaches its limits in these situations. And the good news is machine learning can actually be a viable alternative to this imperative programming. What it does, basically machine learning, is we try to answer questions with our data. I think that's the best and most concise definition that I've ever heard about machine learning. And it already encompasses the two essential parts that we will deal with on a daily basis. One, we do some training. We use data to come up with something where we can learn from, with a model, with something that kind of we get information out of, and we use that information to do the second thing, to do inference, to answer questions. And both of these parts are really important. So a few words on the terminology, because many of these words are frequently flying around and people are not really certain what they mean. So I'll try to explain it to you. First of all, artificial intelligence. Well, artificial intelligence is a really broad word. I would actually say it's more of a marketing term than something that people can actually understand and say what goes into this. So many things go into it, but it's really hard from a technical perspective to say what is artificial intelligence, because it comes down ultimately to say what is intelligence. And well, already people disagree on how to define intelligence and therefore how to say this is artificial intelligence. But in general, anything that does something with knowledge, we could cover under the broad field of artificial intelligence. Technically speaking, a database already would be some sort of artificial intelligence if you store some information there, but if we're within our domain, we typically talk for example, about knowledge-based systems where you can, ask a question and it gives you some sort of answer. So I would honestly try to avoid the term artificial intelligence because it invites a lot of, stuff that we don't want to include. Machine learning is the thing that I honestly prefer most to talk about, because machine learning is exactly what I just told you. Use data to answer questions. And this can be something really simple, a linear regression. So you just have points and you try to fit a curve or a line in that into your data to obtain some information. That is already machine learning. So we use data to answer some questions. For example, if you have the body weight and the height of a person, you can probably fit a curve and find some correlation between these two variables. Inside machine learning, there is a subcategory that is really interesting and that we will be talking a lot, which is representation learning. Here we try to come up with a compact representation of the information that is stored in our data. The most famous example is a neural network, and this is the thing that we will be using a lot. So what we try to do here is come up with a certain set of features that allow us to efficiently answer certain questions. And within representation learning, there is even one more subcategory, which is deep learning. So we're probably mostly dealing with neural networks here. And within these neural networks, if you stack them quite deep, So if you not only have like one or like hundreds of neurons, but millions of neurons that work with each other, we typically speak about deep learning. However, the boundary here is somewhat fuzzy, I would say. So it's not immediately clear where kind of deep learning starts and so on. Talking about meaningful representation, we've already seen the example of cat classifier and dog classifier. And one thing that is a meaningful representation is if we have something like the information that there are eyes and whiskers and a nose in the image, which would probably make it much more likely to be something like a cat than a car. And this is exactly what deep neural networks typically give us. They try to come up with these high-level features. So if you think about the image itself, it's a set of pixels. And we can extract some low-level information, for example, some colors, maybe some lines, edges, but that would be low-level features. And from these things, our network learns by itself to extract more meaningful features in higher levels. In this example, we're given the input pixels. We try to extract, for example, the network learns to extract something like edges, and then corners, contours, and ultimately at the very the highest levels of our neural network, we will probably have some really meaningful neurons that are sort of tuned on a particular piece of information. Imagine sort of you have a car neuron that really becomes active if its input is being fed with information about subparts of the car, tires, windows, whatever. So this is what we use, and this is why these things are so powerful, because this representation here, we don't have to build it ourselves. Deep learning allows us to actually train these things by itself. So we just feed in the image and it learns to extract all of these middle and high level features on its own. So the question you might ask yourself, how does it do this? It's sort of some magic, is it? Well, no, it's not magic. It's you can think of it as math or like linear algebra on steroids. But how it really works is basically you need 3 ingredients for a machine to learn something. First of all, you need a model. You need something where you have a set of operations, of computational rules that somehow do something. That model typically has a bunch of parameters, how it can do these things. And these are the parameters that we will have to tune to make the model work well. Secondly, we need something like a loss. What is a loss function? In our case, it's kind of a navigator which tells us how good we're doing right now. And what do we do with this loss? We feed in some data through our model, and then we compute the loss to say, okay, how good are we right now? Where do we need to improve something? And if we have our certain loss and it tells us, well, we're doing a pretty good job now, we need the third ingredient, which tells us, okay, how do we get better? So initially, each model typically doesn't perform very well, so the loss will be really high. And if we then say, okay, this is my loss, this is how I'm doing now, I'm trying to optimize this with a certain function. Now tell me again, how am I doing? And if you combine these 3 things, you can actually teach a machine to learn something useful. What are these useful things that you can train a machine to learn? For example, image classification. This is one of the most frequently used examples for deep neural networks, where you just try to distinguish between different classes of objects within a single image. Cats versus birds versus dogs, and so on and so forth. This works actually really well already today, but there are still some challenges that we have to solve. Another example where you can use image classification for is in the medical domain. So if you think about if you go to your doctor and he sees some skin lesion, well, he has to take a look at it and try to figure out whether it's a melanoma, which is potentially dangerous, or some benign skin lesion that you don't really have to care about. So this is an image classification problem, actually. And in the last few years, there have been quite a number of ideas and approaches how to train a machine to be able to do this. And imagine the following situation, that if this works really well, and you can, for example, deploy it to work on a smartphone, millions of people would have the option to quickly scan their issues, and then, you know, the thing would tell them, go see a doctor, or, well, this is harmless. You can pretty much ignore it. I'm certain that you can ignore this. There has also been a new survey paper, especially on this problem. It's in the literature section at the end. Feel free to take a look at it. I think it's really interesting to see about this. One thing that I remember about this particular example is you have to be really careful with your data, because when they started this experiment for the first time, they used just images of good and bad skin alterations. And the problem was, whenever there was a malicious melanoma, they had a ruler next to it in the image to measure how big it is. And the classifier didn't learn whether it was good or bad. It actually learned to detect this ruler. But this is something we'll come to back later on. What else can we do with deep neural networks? Object detection. That's a great thing. The left image is what I've been working on. So you have a score of music scores, and you want to find each and every note head and stem and all the objects that are in the image. But of course, you can also use it in natural images, where you try to detect cars for automatic toll payment and that stuff. There are also other regions that are not with images, but with voice and audio. And I think this is a particularly interesting example how Google developed a system that allows to almost naturally converse in a phone call. So let's listen to this.
So how can I help you?
Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd.
Sure, give me 1 second.
Mm-hmm.
Sure, what time are you looking for around?
At 12 p.m.
We do not have a 12 p.m. available. The closest we have to that is a 1:15.
Do you have anything between 10 a.m. and 12 p.m.?
Depending on what service she would like. What service is she looking for?
Just a woman's haircut for now.
Okay, we have a 10 o'clock.
10 a.m. is fine.
Okay, what's her first name?
The first name is Lisa.
Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd.
Okay, great. Thanks.
Great. Have a great day. Bye.
I think it's amazing how this system works and how these two seemingly human, almost human things communicate with each other. And keep in mind, one of them wasn't a human, was actually a machine that was listening to the incoming audio, translated it into written form, reasoned about what the thing was saying, and then again there was the other end where the response was first generated and then synthesized into audio. So it's a really complex system, but I think it's pretty amazing to see what you can actually do with this. But as with every technology, things sometimes can go wrong. And especially in the United States, there's been almost a plague by automated calls, so-called robocalls. Let's listen to one.
I'm calling about an online request you once made about health insurance coverage.
Okay.
I work with all major companies and compare...
Hey, are you a robot?
What? No, I am a real person. Maybe we have a bad connection. I'm sorry about that.
Will you tell me you're not a robot? Just say I'm not a robot, please.
I am a real person.
I mean, I believe you, but will you just say I'm not a robot? It'll make me feel better to hear you say it.
There is a live person here.
If you could say the words, I'm not a robot, it would really mean a lot to me.
I am a real person. Can you hear me okay?
Right, but will you say I'm not a robot?
Of course, this is a humorous way to take a look at this, but I think this is already showing us that whatever technology we come up with might also be harmful. So we have to really make sure whatever we do is ethically responsible. Another really nice example, I think, is a good inclusion here is music harmonization. So how this works is you have a melody, and to that melody you want to also have the accompaniment, the other voices. In this case, there is a system called Deep Bach, and what they're trying to do is mimic the way how Bach wrote his compositions, or basically how Bach sounds. That's more accurate. So they take the melody of a piece by Bach, and then the system generates all the other voices. And what's really interesting about this, we're going to listen to it first, and then I'm going to tell you something really, really interesting. Sounded pretty good, didn't it? There is an interesting study here that was conducted with that system, and what they did was they asked musicians if a composition was written by Bach or by their machine. And it turned out that it was really, or basically they asked them what they liked better, and it turned out that people actually liked the machine-generated Bach really, really much better than, or at least they couldn't distinguish between these two outputs very well. So I think this is pretty amazing to see a machine doing something like composing in the style of Bach. This is the, I think, most spectacular example that I will present to you this course. It's DeepMind's StarCraft II neural network. So what they're doing here is they're playing StarCraft II. And it's a really fantastic example of all of the tools and things that are going on here. So let's take a look. What they're having built is a machine, Alpha Star in this case, that takes as an input images, frames of the computer game itself, including some information about the environment in such a way that it can process this. To not make this completely unfair, the computer is only allowed to, with a certain number of observations per second and certain number of steps, of moves that it can take per second. So what happens here is that the computer here is currently playing against a world-class champion, Mana, who's competing here, and you can see the different parts. So on the left top side, you see the input that AlphaStar is seeing and the raw observations, kind of a map of the thing. And then it has a neural network, a recurrent neural network that is being fed this information and that outputs certain things, actions that it can do. So it can move around, it can click somewhere, it can order production of units and so on. And what we can also see here is in the top middle section here, something really interesting, the outcome prediction. So how this works is that the computer at each time step tries to predict whether it will win or not. And this is due to some statistics that it knows, for example, the number of units, the resources it has, and so on and so forth. So this outcome prediction here is the loss. So it says, okay, what can I do here if I take a step to improve the probability of me winning? So if I build this unit, will I win or not? And this is a really interesting example because the computer actually beat the human here really in every situation. There was only one kind of bug that a human exploited. So he was able to kind of lure the computer up and down on some border, some edge of the map. And the computer kind of had this failure state where it then was chasing that unit up and down. So he was able in the meantime to destroy the enemy base. But basically the computer was super good in this game and beat that world champion really dramatically, I would say. To sum it up, machine learning can be a viable alternative to imperative programming. Probably the only viable alternative when we think about really challenging tasks like self-driving cars or speech recognition. With the advent of machine learning and deep learning, these challenges have really seen a dramatic boost in performance. Machine learning is, again, using data to answer questions. Keep this in mind. And finally, I think deep learning can do pretty amazing stuff, as you've seen in the previous slides. So I'm looking forward to your projects, and I wish you a nice week and see you soon.